Hey, year 13s! Let's see how long it takes for you guys to arrive. 3 people waiting. Look at that. Wow, that was quick. That was amazing. Say hello in the chat, guys. And I'll do the register. Amazing. Amazing. See how long it takes for you guys to appear. Amazing. There we go. Hey, Naomi. It's so nice to see you. I feel like I haven't seen you guys in ages. Registration. Hey, Josh. There we go. So I've got Naomi. I've got Josh. Got Maxine and Megan. Amazing. Just Jackson now, folks. I think Jackson's going to be here on time. Oh, Markham is missing. I'll crack on. So, guys, we are continuing. Our Unit 4 paper. I am aware that I don't have the booklet that you guys are going to have. So I'm going to be looking up all kinds of entropy values and enthalpy values. These, of course, will be in your booklet, but these are going to be included in your exam paper. You will have a data sheet in it, but it's much shorter. It's only like 5 pages long compared to the 25 pages of the last one. Okay, so I'll share my screen. I will share my screen. There we go. Share. Boom. Done. There we go. Right, I'm going to continue with exam paper 4. Always good. And then I'm going to do paper 5, folks. Oh, can you believe it? I'm going to do a paper 5. Right, hide that. I get rid of my keyboard. There we go. Okay, and we're on. We are on like Donkey Kong. There we go. Okay, switch to tablet mode now. Right, this is the paper we were doing. We were working through October 2018, paper 4. Managed to get through all of the multiple choice and onto the long answer. Okay, right. This is where we got up to. Predict the sign of the entropy, decomposition, justify your answers. I like it. Good. So, calculate the entropy change of the system, for the decomposition of 2 moles of, give the sign and units with your answers, use the data from page 2 of your booklets, yada, yada, yada. Right, so I need the equation, the equation's there. So annoyingly, I'm actually going to write out my equation again. 2Na N3 going to 2Na plus 3N2s. I like it. So the standard mole entropy change, calculate the entropy of the system. So as soon as I see system, we're running super. Yeah, delta S equals products minus reactants. Just to let you know, by the way, for lots of exam boards, if you don't take an Excel, the mark would actually be for writing out delta S system equals the sum of the delta S products minus the sum of delta S reactants. I never like, whenever I do super, I'm always a bit, that will lose you a mark. It's not clear enough. You have to do this whole sum of malarkey. So, okay, let's divide it in 2. So it's given us the entropy of sodium azide. It's given us this one at plus 70.5. And we need to do products minus reactants. We need to look up the value for that one and that one. Now, this is sodium solid and nitrogen gas. So we now need to just going to quickly check that. Yeah, solid and gas. So I'm now going to look up those values. Yeah. So I'm going to go sodium entropy value. Isn't that interesting? Sodium entropy. Let's do that. Standard entropy of sodium solid. It would actually be probably beneficial. This is where it's very tricky, this, isn't it? Entropy of sodium intakes. We can. I don't really like that. It's probably going to be the first one in webbook. I'm very aware that this is going to slow me down massively. Yeah, sodium as a solid. Entropy values. There you go. Condensed phase thermochemistry data. So there you go. Entropy of solid. It's giving you pressures and a liquid. It's really interesting. So we've got 50.46. 51, sorry. That there is 51 51.46, and it's a positive value, of course. All entropies are. The only way you can get negative, you can't get negative entropy. Yeah, the lowest you can get is 0, and that's at absolute 0. Now we need to look up, what was the other one? N2 gas. So let's look up N2 gas entropy. So this is nitrogen entropy. As I said, these will be provided to you. These will either be in your, oh, look at that, molar and standard molar entropy. 153.3. 153.3, which makes sense. It makes great sense, 153.3, because it's a gas. Right, so we now need to do super. So we're going to say, let's do the products first. Let's do sum of delta S. It's such a habit of writing delta H. Delta S products is going to be 2 times 51.46 plus brackets 3 times 153.3. Realizing that we've got to multiply them up by their from the ratios, the stoichiometric ratios in the equation. 2 times, it's a mild butter calculator on, brackets, 2 times 51.46, close brackets. Missed the 1 on the calculator. I think I've got a dodgy number 1. 51.46 plus brackets, no, close brackets, plus brackets, 3 times 153.3, close brackets. I missed the 3, 0.3, there we go. And I get a total for that one is plus 562.82. Yeah. Next, I'm going to do delta S reactants, and that's easy, which is 2 times 70.5. So 70.5 times 2 is 141, 141, plus value in front. Right, now I apply super. Yeah. So I'm going to do products, which is plus 562.82 minus 141. Yeah, there's a, by the way, I'm in the enthalpy mode. So I'm going to do plus 562.82 in brackets, minus brackets, plus, I know you hate it, mathematicians in the room, but I just prefer it. I know you hate it. So plus brackets, plus 562.82, close brackets, minus brackets, plus 141. And I do know what that's going to do anyway, but we're going to have plus 421.82. There we go. And you don't forget to give it units. Joules per Kelvin per mole. There we go. Next. Seems reasonable. Massive increase in entropy, making a bucket load of gas. Yeah, very reasonable. Next, calculate the entropy change of the surroundings. Right. So straight away, entropy is delta S surroundings equals minus delta H over T. Yeah. So we need to find out what the enthalpy is for the reaction, which is probably given in the equation. There's my enthalpy. Minus 42.6. So I can go, therefore, delta S sur equals minus brackets minus. That was the trick. Naomi caught me on the hop on that one. 42.6. Yeah, Naomi caught me on the hop. And it says at 298. So let's do 298. So minus brackets minus 42.6 all over 298. So I'm going to have an entropy of the surroundings is going to equal 0.142. It's actually 43, isn't it? 3 sig fig. 43. Right, and again, give its units. Well, now this is kind of a nice thing here. Does it say give its units? Not really. Yeah. So this one's going to be in kilojoules. You've got to watch out for this, because what I put in here is I put in kilojoules. Yeah, because the kilojoules was up here in the equation. There's my kilojoules. So this is going to be kilojoules per Kelvin. Yeah. Kilojoules per Kelvin. Is this going to be per mole? Technically, it's actually not. Yeah, because the problem is the reaction's gone twice. Oh, no. Is that going to matter? Do I have to divide that by 2? Ooh. No. Oh, decomposition of 2 moles. So it's correct. Kilojoules per Kelvin, and that's it. Yeah, because that was 4.2. It would be hot, Mr. Duncan, for the delta S of nitrogen. It should be 6 or of it not 3. Oh, have I typed in a number wrong? Have I typed in a number wrong? What number have I gone and typed in wrong? For the delta S of nitrogen, have I typed in the wrong number? Molar entropy, 153.3. What have I done? Because it's per mole, not atoms. Oh, have I gone? Let's click on this. It's very unusual for it to give me the molar entropy as a gas. Oh, it's giving me different figures. This is why I really need to use Databook. Do you know what? This is a nightmare, isn't it? Because otherwise I'm going to end with all kinds of crazy numbers. Right, so I need to download your Databook. Let's see if I can get your Databook. Google, why not? No, you don't do per atom. No, because it's per mole of atoms. The entropy. Hang on a minute. We need your Databook. We need your Databook here, folks. I've made a mistake. Let's just go IAL chemistry. I'll have to reorganize the dial. IAL. Oh, what are you doing? IAL. If I press space and finish, no. IAL chemistry Databook. The problem. This is the issue I'm going to have, of course, with these particular questions. Let's go for that one. I feel like that's not going to be the correct one, but we can try. Your Databook is right at the end of your specification, and this is the new one, I think. See if I can go all the way down to the bottom and find your Databook. This is an issue, guys, that we're always going to have here when I'm having to do these questions and I haven't got the Databook on hand. I just need to make sure I've got it on hand, don't I? Not the best. I'm sorry, folks, about this. I should have been more prepared. Right. Infrared spectroscopy. Avogadro. Wow, they give you Avogadro's number. Are they going to give me entropy values? I've got a feeling they won't. Give us equations, periodic table. No. Data. That means it's going to be in the other book. It's on our classroom, isn't it? It's on our classroom. Hang on. Sorry, guys. This will be. This is just going to be an issue here. Data booklet. Chemistry data booklet. Let's go. It's going to be the new one. We need the old one. 2018? No, that's the new one. Eek. I've gone and lost it. I want the old specification, not the new one. Chemistry. Oh, right there. 2013. Course materials. Yes. Where's right specification? Changes to mark scheme. Where's the students' workbook? No. Sample assessment, teaching and learning exam materials. Are they going to give us the data book? Modified papers. Oh dear, it's not going to give me what I want. Is it teaching and learning materials? Data booklet. Right, let's download this, shall we, folks? Download. There we go, and I'll put that in. I'm going to put that on my desktop, make it easy for me to find. Right, let's try this again, shall we? Right. Let's have a look. IAL. Right. Entropy values. Oh no. I can't turn pages. Or can I? Oh! I can. That's cool. Right. Nitrogen. There. It's number 7. Yeah, nitrogen. N2. Yeah, you see it's in a pair. Its entropy value for a gas is what they wanted me to do was 95.8. What did I use? Oh, way too high. Have I got that wrong? That's entropy. Thermochemical data. Yeah, it all seems reasonable. Gas. Yeah, 95.8 is what they want me to use. Why have I got 158? It's weird. It's that one there, folks. 95.8. So I've definitely got the wrong number. 95.8. Okay, input that then. There you go, folks. 95.8. Redo my maths. Gonna redo my maths. Yeah, 2 on calculator. 51.46 times 2. Yeah, and then plus brackets 3 times 95.8. So, okay, my actual number there should have been plus 390.32. That means I ought to find sodiums as well. If I'm going to do this, guys, I better do it properly. Where's sodium? Sodium's down here. 1 is a solid. Entropy is 51.2. What did I use? 51. Okay, there you go. Round it up. I like it. 51.2. There you go. I'll get rid of all that number again and do it again. So 51.2 plus 51.2 plus 95.8 times 3. So I get 389.8. Yeah, kilojoule. No, hang on. Joules per Kelvin per mole. And it has to have a plus sign. Joules per Kelvin per mole. Right, now I can put that number back in here. Yeah. Let's get rid of that. So 389.8. Right, so 389.8 minus 141. Agreed? And I get an answer of completely different from what I had. 248.8. It's a plus sign, and that is going to still be for surroundings. Yeah, joules per Kelvin per mole. Yeah. Maybe it should be 6. Why 6? No, it shouldn't be. It shouldn't be. Shouldn't be 6. Because look, on the data sheet, it gives the N number, yeah, which says 2. There, N2, like O2. It shouldn't be times by, it shouldn't be. It should be times by 3. That there is a molecular entropy value, not an atomic entropy value. Look, P4, yeah. It shouldn't be. Let's check the mark scheme. Since we're there, let's do the mark scheme since you guys are on this. Yeah. I get these from Save My Exams. Save My Exams Chemistry. Go on to the, I don't know, that one maybe. Guys, I'm always happy. I am as human as the next person. I'm as fallible as the next person. So it's definitely worth me spending the time doing this. So A level, and then go chemistry, and then Edexcel, past papers. We are in October. Shouldn't be 6. It's not times by 6. Shouldn't be. Oh, does that not work? Not unless it's here. No. Oh, A level. Chemistry, that's CIE. Edexcel chemistry, past papers. Laptop's just running a bit slow, I think, today. Let's check our mark schemes. I kind of assumed that you guys would have the mark scheme running there. So June, oh, we're doing 2018. Oh, there you go. June 18. Oh, is there no October 18? Oh, which one am I doing? June, July. I'm doing October. Is that correct? Where do I find the mark scheme for this guy? Where did I get this from? Did I get this from PMT? October 2018. Where did I get this paper from? Don't know. Oh, hang on. Hey, no, I'm in the wrong one here, guys. It should be international, should it not? Yeah, you guys have 6 papers. A-level chemistry. I've gone and made a mistake. International past papers. There. Sorry, this is my fault. Give me a sec. I think my laptop's taking a while to do anything. It should be 6. Why? It shouldn't be. In my eyes, it shouldn't be. That's not what I clicked on. What are you doing, you stupid laptop? A-level, Edexcel, Edexcel International, past papers. It shouldn't be. On the data booklet, it says the mole applies to single atoms. No, it doesn't. Look at the data booklet. On the data book, it says standard molar entropy at 298. It doesn't. It says it's diatomic. Where's the mark scheme? Unit 4. I want to see it. I'm happy to say if I'm wrong, but I have never done it like that. You wouldn't take you can't take the entropy of a single atom because it's not a single atom. It's diatomic. The entropy would be way too high. Way too high. It doesn't. You're wrong. I'll bet my life on it. I'll bet my life on it. 6 times. It does actually say that on the mark scheme. I don't know why. 2 times and then 6 is at what? Half at O. Half N2 per atom. How bizarre. Maybe that's why my value was so small. Huh. Data booklet. For this table, the mole applies to single atoms. Oh, that sucks. That's what it does, is it sucks. There you go. I stand corrected, folks. I bet my life I'm dead. Kill me now. It's fine. No. So it's 6. Yeah, happy to make the correction. I'll bear that in mind next time. Below that delta atomization. Yeah, it's the same value. No, that's breaking bonds. That's different. But, okay, I'm happy to make the correction. Happy to. Yeah, 51.2 times 2 plus 6 times 95.8. That's horrible, that. 6 plus 6772.2. Yeah, so then put that number in here, 677.2, minus that value. Fine. Plus 677.2, minus 141. So the answer is plus 536.2 joules per Kelvin per mole. So is that the correct answer on the mark scheme? That sucks. 536.2. Fine. Okay. Mental note. Good to know. It's good to know. Make an adaptation. Right. Okay. So is this one all reasonable? Use your answer to calculate the total entropy change for the total. So delta S tot equals delta S cis plus delta S surroundings. Yeah, add the numbers in. So I've got plus 536.2 plus 0.143. I'm surprised that it's so. Oh, you can't do that. Can't do it. It's in that's in kilojoules. That's in joules. Trap. Yeah, times that by 1,000. Times that one by 1,000 first. Yeah. So 536.2 plus 143 gives me total entropy change is plus 679.2 joules per Kelvin per mole. Joules per Kelvin per mole. Mark scheme, and I don't trust myself now at all. It's been a nightmare. There you go. Either way, whichever one you get, yeah, divide it up, times it up, whatever. 143. Oh, hang on. What have I just managed to do? What have I just managed to do? Am I not reading something? There you go. Sorry. Plus 79.2. I'm wondering if they mind about the fact that there's more decimal places. So technically it'd be rounded up to 80, 680. Do they allow 680? What do they allow? Anyway, fine. Positive value must be there. I'm just wondering, note, TE on incorrect expression. Ignore significant figures except for 1. So it's fine, we're good. Okay. Next. When an airbag is deployed, the chemical reaction produces a rapid rise in temperature to about 300 Celsius. By considering the molar entropies of the substances involved, explain the effect, if any, that this higher temperature will have on the entropy change of the system for this decomposition. Right. So we know that delta S system, delta S system is super, Yeah, P minus R. Yeah, so what's that going to do? Products minus reactants. So what's going to happen is we realize that the entropy is actually going to increase. The products, the sodium will be liquid, so that will increase it. The sodium azide will have started off as solid. It'll make it larger. At that temperature, the sodium melts. Do I have to justify it? By considering the molar of the substances involved, explain the effect, if any, that this had on the entropy change of the system. Okay, so I'm going to say it will increase it. Increase entropy of system. Increase delta S sys. The reason being is at this temperature. At this temp, I'd love to know what the boiling temperature was of sodium. Sodium's going to be at least a liquid. Data sheet. Hang on a minute, where's sodium? They'll be able to tell us. Yeah, where's sodium? Find sodium. There it is. So sodium has a melting point in Kelvin of, but boiling point, so it's turned into a liquid but not a gas. That's nice to know. So at this temperature, Na is liquid. So products will have higher entropy, but not by a huge amount. I'd love to actually see if the data sheet tells me that. So it's given us the entropy in its standard state, not for when it's a liquid. But we know that there's always an increase. There tends to be low figures for solids. Yeah, they're in like the 20s and 30s. Liquids tend to be the 50s or 60s or 70s, and then the gases are in the hundreds. So product will have higher entropy. And then products minus, oh, hang on. Yeah, so bigger number, but the reactants are still the same. Yeah. So larger. Oh, hang on a minute. Products minus, oh, I've made a mistake because the products is bigger. If that was 10 minus 5 originally, and then the products are larger, 15 minus 5. Yeah, it means the overall change is going to be larger. Yeah, larger product entropy. But reactants stay the same. I want to see what the mark scheme says. I want to go straight to the mark scheme and see exactly what they want me to word, how they want me to word that. Right. The entropy of the substance always increases because of positive increase. The molar entropy of gas increases the most with temperature. There are more moles of product than reactant. I don't know how that will make any difference. Sodium changes from solid to liquid. There you go. So system must increase. So they just want you to say that at a higher temperature, entropy always increases. Okay. Fine. So I'll miss the first mark. So I'll definitely say temperature. This is me to do. I'm going to do this in red to show that I need to make sure that I always mention that. Entropy is always a nightmare, folks. Increase temp, increase entropy. Yeah, delta S. There we go. So that was the mark I missed, but definitely get that one. Larger product entropy. Yeah, so entropy of the system will increase. That's fine. I'll get that one. Okay, acid-base theory. When citric acid is dissolved in water, only one proton molecule ionizes significantly. Give 2 reasons for this. Okay, so first reason, once a proton leaves, the molecule will become positively charged. That's actually the answer. That'll give it to me. Will become positively charged. So more difficult to lose second proton. Also, what else is going to happen? What's the second reason? Yeah, pushes the equilibrium back to the right. Why does entropy always increase in temperature? Good question. So we know that temperature temp is a measure of vibration. Yeah, is a measure of vibration. If you have, yeah, so if I have this particle, yeah, and then I heat it up, add heat, and it becomes this. Yeah, let's give them faces. Yeah, there you go. Yeah, so as you increase temperature, vibration increases. But what we also know is that entropy is a measure of disorder. Measure of disorder. And we know that if you've got particles like this, yeah, they are going to have much more order than if, yeah, these guys are going to be far more chaotic. Yeah, we know that. So since temperature, there we go. Yeah, more chaos. You need to know the graph for it. Yeah. So if you increase temp, yeah, you get this graph. Starts at absolute zero. Yeah, at 0 Kelvin. 0 Kelvin, you have zero disorder. This is a measure of disorder in joules per Kelvin per mole. Joules per Kelvin per mole. And we know that at 0 Kelvin, we have zero entropy. It's the only time it does. The graph will increase, yeah, and then it suddenly jumps. And this little rise here is because melting has just occurred, yeah. And then we get another steady increase, and then a big jump, yeah. And this is because of boiling. We're becoming a gas. Big increase in entropy, yeah. So the particles go from down here with low energy to having more energy, then to being a liquid, and being able to move over each other, and then they still gain more energy. Yeah, so you realize that entropy is a measure of, you could almost link it straight to vibrations. It's more complicated than that. There's different types of entropies in reality. Yeah, vibrational, translational, rotational, etc. Next one is that the equilibrium is being pushed. Because if we to lose a second one, it means there could be a higher concentration. You'd also say that the bonds are going to therefore increase in strength. Yeah, but I won't. I'm just going to say H plus conc in water increases. Increase pushes equilibria to left. Want to see the mark scheme? These are hard, folks. We always know these are hard, though. There we go. Explanation of Ka1 value. As pKa increases, acid strength increases. That doesn't absolutely. Effect of first dissociation. Relatively high concentration suppresses second further ionization. There you go. Equilibrium shifts to the left. Yeah, ionization reference to third. Yeah, ignore. Ignore reference to ionization energy. First ion suppresses weakened second ionization energy, or ionization removes proton, forming a negative ion which requires more energy. That's so okay. But I haven't mentioned pKa. They wanted me to mention pKa, folks. And because the data's there. I think it's a swindle. Yeah, if they give you data, you must quote data though. Yeah. So you would say pKa, you just have to say pKa1 is less than pKa, should be up there. pKa1 is less than pKa2. This is why, guys, this is a great example of, by the way, I'm going to add that in red because I forgot it. If they give you data, use the data. Yeah. I don't agree, that's not an explanation in my eyes, but throw it out there. Write the equation for the first dissociation of citric acid using H3A, okay? H3A equilibrium, H2A minus and H plus. State symbols are not required. Winner. Thanks very much. Next, the pH of the solution was 1.8. Calculate the concentration of mole per dm cubed of the solution. Assume that the acidity is only due to the first dissociation of citric acid. Okay, I like that. It's weak acid. So Ka equals products. And I'm just going to do HA2. Shouldn't do it, but I'm going to. Over H3A. There we go. Right. So we know the pH. Got that one? That's great. This is always the pH, remember that. Yeah, so the first thing I'm going to do is shift anti-log minus the pH. That's going to give me the H plus concentration. So on the calculator, shift log minus 1.98 is going to give me 0.0105 moles per dm cubed, yeah, H plus ions. I like it. Right, so now what we can do is we can say that these two are the same. So Ka equals H plus squared all over H3A. Reorganize, bring that up, bring that down. So the concentration of H3A is going to be equal to the concentration of H plus squared, which we've now just worked out, yeah, all over the Ka value. What was the Ka value? Now, remember, they've given us, this is a trap as well, they've given us a pKa value, which means we've got to shift that out of log as well, yeah? So I need to go pKa equals 3.13, and I'm going to go 10 to the minus 3.13 to get it out of pKa into Ka. So shift log minus 3.13. I think it's a bit of a mean thing, that, because they're making you do two things twice. Shift eng gives, shift eng, there we go, which equals, I'm not going to bother. I'm going to get 0.741 times 10 to the minus 3. Right, so there's the Ka value, that's the Ka value. Put that in there. So concentration of that equals 0.0105 squared all over 0.741 times 10 to the minus 3. 0.0105 squared divided by answer gives me, so the concentration is 0.149 moles per dm cubed. And I'm done. Let's check it. It's the rounding I'm worried about. Oh, there we go. Fine. Notice that this one is not worth anything. Yeah, the false equation, taught you this in a lesson, the false equation is not worth anything, but at least 0.149. I like it. We're done. Winner. Tick, tick. So there's a mark for this original equation. Yeah. Then there's no mark for that one. There's a mark for that guy. Yeah, and then final answer at the end. Kind of get the point. Next, the concentration of citric acid in lemon juice was determined by a class of students, each with the following procedure. Give a reason for removing pulp from the lemon juice. Squeeze the lemons and sieve the lemon juice to remove the pulp. We're reacting the citric acid with sodium hydroxide. Pulp. Pulp may contain a different acid. Oh, hang on a minute. Well, it'd be mercury, wouldn't it? What am I write down for that? Where's it going? Measure 25 centimeters cubed of lemon juice in a volumetric flask. Using a pipette to make up the volume to the mark with distilled water and mix the solution. You can't pipette it. It'll get stuck in the pipette. That's really interesting. I'm going to change my answer. Yeah, solid pulp. Solid pulp would block pipette. Yeah. Using a pipette of the distilled solution, diluted solution to a conical flask. You couldn't do that. Yeah, it would block pipette, and they didn't even call it a graduated. Nightmare. Name a suitable indicator for the titration. It's a weak acid, strong base. You can use phenolphthalein. The only time you use methyl orange is weak base. Yeah, so phenolphthalein. Oh, give your choice on the data book. Oh, interesting. Well, I don't even need it. The choice is phenolphthalein. Phenol, PH-THALEIN, phenolphthalein indicator. Yeah, my choice is because, look at the graph. Yeah, the graph, weak acid. Yeah, weak acids, we're going to start at 3. start at 3 on the pH scale. We're going to add sodium hydroxide. Yeah, we're going to get this lip up. Yeah, and then it levels off. This is the buffer region. And then we get this vertical. Yeah, so the vertical region is above 7. There's 7, and the equivalence point is 9. Yeah, so I'm going to say the range is above 7. Indicator range above 7. I'll get the marks for that. I don't actually need my data booklet for that one. Definitely not. Pulp could block the bet. There we go. Pulp causes side reactions. Reject. Reject. I nearly did that one, folks. Nearly did it. It was a practical question rather than a chemistry question. Stupid. Indicator range should roughly the midpoint of 6.7 pH of the second buffer region at what? Indicator range needs to be from 6 to 9, yeah, to 8, 10 to 13. Oh. Anyway, yeah, it's fine. Just give the indicator range. Quote from the thing. It's fine. One student carried out this titration using sodium hydroxide with a concentration and obtained a mean tide of 19.65. Calculate the concentration in grams per dm cubed. Good old GCSE trick there, coming into right at the end. 5 from the original lemon juice. Right, so we know that the H3A with sodium hydroxide, not even going to bother with the next thing, is a 3-to-1 ratio. Yeah, that's a bit of a nightmare, isn't it? So it's in a 3-to-1. Okay, so sodium, so moles. Step 1, get to moles. Concentration, volume. Number of moles is C times V over 1,000. Yeah, concentration 0.095 multiplied by a volume of 19.65 all over 1,000 equals 0.095 multiplied by 19.65. Oh, I typed in the wrong number. 0.095 multiplied by 19.65 divided by 1,000. And I get 1.87 times 10 to the minus 3. Can I keep it on my calculator? Right, step 2 is the ratio. So the ratio is a 3-to-1 or 1-to-3, and we're moving in this direction. So we're going to divide by 3. Yeah, divide that by 3. Gives me 6.223. It's interesting. Times 10 to the minus 4. Yeah. And that's moles of H3A. Now remember, this is in the diluted 25, folks. Watch out, it's a trap. Yeah, because it says in the original in bold. Yeah, they took a 25 centimeter sample, didn't they? Measured 12 lemon juice into a 250, so they diluted it, so it's a factor of 10. So I need to do it times by 10 here to get it back to the original. I don't know why I wrote down 3. Times by 10, so 6.223 times 10 to the minus 3 moles of H3A in original. I'll put ORI. Right, what was the original volume, which was 25 centimeters cubed? Yeah, would everyone agree? That's weird. Gave a totally different set of numbers. Bizarre. Right, so I now need to number of moles. That's the moles, and it was in 25. Number of moles times I'm just going to reorganize, speed it up a bit. Times 1,000 over 25 gives me C. Yeah, times. I've got to times by 10 first, because I didn't do it on my calculator. Times by 1,000 divided by 25. The original concentration is 0.249 moles per dm cubed. Right, now I need to get the grams per dm cubed. Number of moles is grams over rams. I'm not changing the dm. The dm isn't changing, just need to make moles to grams. So moles to grams, I need to bring rams over times by the rams. Have they given us the molecular mass of citric acid? Have they? No, they haven't. So they're actually wanting us to do that? Wow, all right, fine. So I now need to work out the RUM's relative molecular mass of citric acid. There's the formula. Easier to deal with that one, isn't it, folks? So 12 times 6 plus 8 plus 16 times 7, 192 for citric acid. Yeah, so that's multiply that by 192.0. Don't forget, you're at A level. Times by 0.249, and I get 47.8 grams per dm cubed, and there's my answer. Let's check it. Oh, that's interesting. 92 should be 0.0, should be, there's, they've made a mistake. They're saying that I've used a rounded number. Yeah, okay. I wonder how much just an answer times MR. Anyway, not that it really matters. Done. And down times 40. Fine. So I've got a round. I've picked up a rounding error, haven't I? Although theirs does round to 3 sig vig to 47.8. It still does. Theirs rounds up anyway. So I'm going to give it to myself. It's good. Not unless it says give it to like 5 significant figures, which it doesn't. When the student compared, so I'm just going to, yeah, okay, that's fine. It's absolutely fine. When the student compared the concentration of citric acid from their experiment, they found that the variation was greater than expected. From the uncertainties in the experiment, suggest a reason for this. You're extracting it, you don't know where the citric acid is within the lemon. Yeah, you're taking different samples. Samples of lemon juice will vary. Samples of lemon juice will vary. Acid may be in pulp. Acid may be in pulp. Yeah, don't know. That's a horrible reason. It's because it's lemons. Then that's the lemons are gonna have like, if you squeeze it, you don't know how much you're gonna get out. Citric acid content varies from different lemons. There you go. Reference to errors and uncertainty, that's fine. So varies in different. Oh, they've said they've done it with different lemons. Samples of lemon juice will vary. There you go. Acid may be in pulp. Yeah, don't need that bit. I don't like that bit. Yeah, different lemons, different amounts. Diff lemons. I'll add that in red. It's nice to know. Next, sodium dihydrogen citrate. State the meaning of the term buffer. A solution that resists changes in pH on addition of small amounts of acid or base. Done. Nice and easy. State the pH of a buffer solution containing equal moles of citric acid and sodium citrate. Ooh, equal moles. Ka equals H plus. H plus times A minus. It's actually a sodium dihydrogen citrate. Okay, yeah. So H. Okay, yeah. H2A minus over H3A. So they're saying equal moles. They cancel. pH equals pKa. What was the Ka value? What was the first? 3.13. Minus log. It's clever, isn't it? Minus log 3.13. Log minus log 3.13. Oh. Minus log 3.13. pH? Oh, that's interesting. What have I done there? Oh no, pH equals pKa. Oh, it's already done for me. 3.13. There you go, done. Check the mark scheme. I clicked the wrong button. The mark scheme, 3.13. There you go. Explain how a buffer solution containing citric acid and sodium citrate acts as a buffer. When you add what? I don't know. Oh, and look at that. I've got to the end of part 1 at this point. It was all the data book's fault. Ruined it. Okay, so when small amount, I'll zoom in. When a small amount of acid is added, the sodium, I just want to write a formula after it. The sodium dihydrogen citrate reacts with it, reacts with H plus, removing it from system, equilibrium shifts, keeping ratio of citric acid, it's a lot of white in it, citric acid and dihydrogen citrate almost constant. Reverse. I don't even want to bother with the reverse process. I bet that'll probably just do it. Are present in high concentrations, so their values do not change significantly on small amounts. Large amounts excess for high concentrations. When acid M2 Mark II, when acid is added, is protonated reacts removing it from the solution. When alkali is added, you have to do the alkali bit as well. Yeah, maybe M2 and 3, just give the equation. Yeah. Ignore reference to ratio. Interesting. So they just want you to describe them being in a large reservoir, followed by the reaction of the acetyls removing it from the solution for both. That's it. I'll have to add that. A buffer has a large reservoir of ions. And then write the equation. Oh, look at that. End of part 2. There we go. I'll end it there, folks, today. Since it's taken me so long to sort out that first bit. Made a mess of it. Hello! Hey, you 13s. How's it going? Guys, I apologize, but these things are always tough. My data book values, I absolutely need to make that amendment, recognizing that the data book says per atom, which is a nightmare. It's half a mole of nitrogen. Don't like it. It's not usually the data I'm given, but it'll be interesting to see the difference in your new data book and that one. Something to bear in mind there. Otherwise, I will leave you guys be. I will finish this off next time. I'll see you soon, guys.